All right. Wow, you guys are way on top of this stuff. That's great. Okay. Thank you to those who emailed me. Yeah, I'm sorry that we're getting started just a few minutes late today. My other Calc 1 class went over just by a few minutes because they were having some trouble with a few of these concepts and I wasn't watching time carefully enough. But of course, yes, we do have class today. Thank you guys again for reminding me. And let's go ahead and jump into it. So you don't need to see my email, but you do need to see this. That class went over because today is an exciting day. For them, I had to spend a good deal of time reviewing algebra. I don't think we will have that same problem, so there's not going to be an issue with finishing the content. But I'm excited to show you what we're going to be looking at. So this is MAC2311, section OH1. It's a lecture, and the date is the 11th of January, 2021. Today, we'll be talking about limit laws. This is section 2.3. And if there is enough time, we will also discuss continuity, which is section 2.5. Now, in between these, ooh, that focus is way out of there. All right, here we go. So limit laws are the main topic for today. Continuity we will be getting to if there is time. You notice there's a section skipped in between those, section 2.4, which is the section on the rigorous or precise definition of a limit. That section we're going to spend a full day on, and we'll do that on Wednesday of this week. It's a tricky section, and before we go there, I just want to make sure that we're all a little bit comfortable with the intuitive idea of a limit. And we spent a good deal of time talking about that last week. But I think it's helpful to see these things in context a little bit more before you get into the actual nuts and bolts, because that 2.4 delta epsilon stuff, one, is quite challenging. And two, it really isn't how we go about calculating limits most of the time. Most of the time we'll be using these limit laws and the theorems that I'll discuss with you today. So in order to avoid wasting any more time, here is the theorem with which we begin. These are the limit laws. You can find these in your textbook on page 96. I will be giving you a kind of condensed version because I feel like they're really verbose here, more so than they need to be. But assuming that both the limit as x approaches c of f of x and the limit as x approaches c of g of x exist, we have the following facts. First, the limit as x approaches c of a sum f of x plus g of x is equal to the sum of the limits. The limit as x approaches c of f of x plus the limit as x approaches c of g of x. Right? So if you know both of these guys, and you want to find a limit of a sum of two guys whose limits are known, that's fine. You just take each limit on its own and add them up. And if it works for addition, it works for subtraction. So this is our first limit law. It says if you can calculate the limit of the first piece and you can calculate the limit of the second piece, then the limit of the sum or the difference you just find by taking that first piece and taking that second piece and adding or subtracting them as the formula calls for. Our second limit law says if k is a constant, then the limit as x approaches c of k times f of x is the same as k times the limit as x approaches c of f of x. like so. In other words, if you know the limit of f of x, then you also know the limit of 2 times f of x, 7 times f of x, pi times f of x. Constant multiples play nice with limits. A neat fact, I wouldn't tell this to a non-honors class, but a neat fact is that these two things together make the limit what's called a linear operator. Anybody here have interest in quantum physics? I won't stay too long on this then. Quantum physics is all about the study of linear operators. That's the whole game. Once you fully understand linear operators, you are ready to fully understand quantum physics. The limit is an example of a linear operator. And these two things together are that statement. But limit is a lot more than a linear operator. It plays nice with respect to a bunch of other algebra operations. In particular, it plays nice with multiplication. So if you know the limit of f and g each on their own, and you want to find the limit of f times g, you can calculate that by first taking the limit of f and multiplying that by the limit of g. Again, this is only, you're going to the same c value here. This limit is at the same place. So if you want to find the limit as x approaches 1 of some function times some other function, take the limit as x approaches 1 of the first and multiply it by the limit as x approaches 1 of the second. That's all we're saying here. In other words, limits kind of play nice or split up nicely over multiplication. And if it works for multiplication, it works for division. So if you want to find a limit of a ratio, you can take the limit of the top and the limit of the bottom separately. This one has a little warning that comes along with it, though. This is only kosher as long as the limit of the bottom is non-zero. Right? If the thing downstairs is 0, then this split doesn't make sense. Doesn't necessarily mean that you can't find this limit, just means you can't find the limit in this way. You have to do something else. These are the basic ones. But the book does go on to give a bunch of others. And I'm going to show you a kind of condensed version of those others, because a lot of the things they say overlap in ways that aren't useful. Some combinations or special cases. Combinations of the above give I'll call this 5. The limit as x approaches c of some power, f of x raised to the p, is the same as the limit of f of x all raised to the p. And let's see, I'd like to squeeze in 2 more here. Let me call these special cases. The limit as x goes to c of x itself is just c. And I'll use this symbol for the word and a lot. This is called an ampersand. And as long as c to the p is defined, the limit as x goes to c of x to the p will be c to the p. So believe it or not, the items down below are consequences of the 4 items above, but I'm not going to go through the details to prove those. If you wanted to prove 5, you would take number 3 here, where f of x and g of x are the same function, right? If f and g are the same, then this would say f of x times f of x, which is f of x squared. And this limit would say that the limit of f of x squared is the same as the limit of f of x times the limit of f of x, which is the square of the limit of f of x. And then you use what's called mathematical induction to extend from powers being 1 and 2 to 3, 4, 5, 6, and anything else. The fact that the limit as x approaches c of x is c is a consequence of the graph, really. You can think of the graph of f of x equals x. It's just that line y equals x. So of course, as the x values go somewhere, the y values go there as well. And then this guy is the fact that this limit is c put together with the fact that powers play nice with limits. I'll give you a second to write this down, and then we're going to prove a little mini theorem connected to this. Then I'm going to show you some examples. We'll start with easy examples and build up to harder ones. So take a second, make sure you get everything down here exactly as I have it written. And we'll move on in about 30 seconds.
Professor Falsticker, what does it say after the ampersand? It's a little small.
There's a constant, where did I use that? And as long as c to the p is defined. So like, 0 to the negative 1 is not defined, right? That's 1 over 0. So as long as c to the p is defined, we can take this limit just by plugging in. But the words here are as long as, and then c to the p is defined.
Thank you.
About 10 seconds. All right, moving on. Let's prove a little mini theorem. If f of x is a polynomial, then for any real number c, we have the limit as x approaches c of f of x is equal to f of c. In other words, you can calculate limits of polynomials just by plugging in the number where you're trying to take the limit. How could I prove this? All right, mathematicians, contrary to popular belief, mathematicians don't give a shit about calculations. We loathe calculation. We like to prove theorems. That's what we're about. So when we see a statement like this, which says, for any type of function, something is true, we want to come up with a proof. How could we prove a statement like this? Any ideas? Well, I'm making a statement about any polynomial. So I should begin with an arbitrary polynomial. Let f of x be a polynomial. That means f of x can be written in the form f of x equals, we remember the definition of a polynomial, an x to the n plus an minus 1 x to the n minus 1 plus an minus 2 x to the n minus 2, and so on, until you get down to a1x, and then the constant term a0, where an minus 1, an minus 2, all of these numbers, a1, a0, are constants. Right, that's what a polynomial is. A polynomial is powers of x times constants all added up. This would be a polynomial of degree n, as long as an, this first constant, is not 0. What I want to show is that the limit of f of x as x approaches c is equal to f of c. That's my goal. So I should write down what the limit as x approaches c of f of x is, and try to show that that's the same as what you get if you just plug c into this formula for f. Is everybody on board so far? Any questions so far?
I'm a bit confused on why the f of x equals an x to the n, and then below, oh wait, never mind, I just figured it out.
That's okay. So this is just the definition of a polynomial, right? Let me, I know it looks weird and scary. It's not how we're quite used to seeing them, because we usually work with specific ones, but define polynomial. I'm going to type blind here. So if we look at the definition of a polynomial, Wikipedia is actually a great source for mathematics stuff. We see that this is just the definition of a polynomial. It's any function that can be written in this form, which is exactly what we have there. So the limit as x approaches c of f of x is by definition the limit as x approaches c of this big expression, an x to the n plus an minus 1 x to the n minus 1 plus an minus 2 x to the n minus 2 plus a1x plus a0. Now, I don't know much about how to work algebraically with limits. Literally all I know are those rules we just wrote on the previous page. Can anybody think of a rule that I could apply to this expression to start trying to break it up and figure out what this limit is? Oh, sorry, that's the recording from my previous class finishing. I want to draw your attention to these plus signs, right? I can think of this as its own little function. An x to the n, that's its own little function. It's a power function. I can think of this as its own little function. I can think of this as its own little function. So I can split this up. I'm going to move to the left a little bit to give myself more space to write. It's the limit as x approaches c of that first guy. plus the limit as x approaches c of the second little guy, plus the limit as x approaches c of the third little guy, oh, n minus 2, x to the n minus 2, and so on. I get my last two terms here, limit x to c, a1 x, plus the limit x to c, a0. So remember, one of our first limit laws is that the limit of f plus g is the limit of f plus the limit of g. I can apply that here to say the limit of this plus this plus this and so on is equal to the limit of the first piece plus the limit of the second piece plus the limit of the third piece, right? That was our very first rule, is that limits split up over addition. Comfy so far? Next, I can pop out those constants. An is a constant. It's multiplying this little function, and I'm trying to take the limit of that constant times that function. So he will pop out, and I get an times the limit as x goes to c of x to the n. And I can do the same in all of these, plus an minus 1, limit x to c, x to the n minus 1, plus an minus 2, limit x to c, x to the n minus 2, and so on. This last guy is going to be a1 times the limit as x goes to c of x. And this last one, you can pop him out if you want. You'd have a0 times the limit as x goes to c of 1. So to go from this line to this line, I say limits split up over addition. That was our very first rule. That was our first limit law. Limits split up over addition. To go from that line to the line below, I use the fact that constant multiples pop out of limits. So I don't want to rip this away from you while you're copying, but that was one of our limit rules as well, that if k is a constant, then the limit of k times f of x is k times the limit of f of x. So in each of these little limits, the constant term can pop out of the limit. Everybody with me so far? Okay, good, good. Now, the last big step here, I'll refer back to these. We use this to split up over addition. We used this to pop out the constants. Now I'm going to use this because in each one of these little limits, I have a limit of a power, a limit of a power, a limit of a power. So this an comes along for the ride. The limit as x approaches c of x to the n is c to the n. Right? That's precisely that last rule I pointed at, that the limit as x approaches c of x to the p is always c to the p. Here the power was n, so the limit as x approaches c of x to the n is just going to be c to the n. Plus. This an minus 1 comes along for the ride. Here the power, p, is n minus 1. So the limit as x approaches c of x to the n minus 1 is going to be c to the n minus 1. And the same thing happens for the rest of these. An minus 2, c to the n minus 2, plus dot 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 a1 c to the 1, or just a1c. And then down here, this last guy, he's a constant. So this will be a0 times the limit as x goes to c of the constant function 1. This limit is just 1. So that's just plus a0 times 1. I won't even write the times 1. When we're trying to prove something, we always begin with something we know is true. The limit as x approaches c of f of x is equal to this limit by definition, because f of x is this by definition, because we're assuming f of x is a polynomial, and all polynomials can be written like this. Then you use whatever tools are at your disposal to try and make this thing more tractable. I know that the limit of f of x is equal to the limit of this big jumbled mess. So let me do whatever I can to understand the limit of this big jumbled mess. Well, I have some rules that I can apply to jumbles like that. That's what we did in these lines. Now we're down here. We've successfully taken our limit. So we should come back in our minds and ask, what were we trying to show, and have we shown it? Have we arrived at a conclusion that is useful and consistent with our goal? What was our goal?
To prove that the limit of f of x as x approaches c is equal to f of c.
Beautiful, right? This was what we wanted to show. Have we shown it? What is f of c? Well, if f of x is this big long thing, then f of c is this big long thing with c plugged in for x. Is that what we have down here?
Yeah.
This is, by definition, f of c. So we're done. We proved that the limit as x approaches c of f of x is equal to this, which is f of c. Victory. Now these proofs are great, but I think we don't really start to understand them until we look at some specific examples. So at first, I'd like to take any questions on the individual steps here, or how we knew any one thing was any one other thing. But then I'm going to show some examples. Questions on the proof. Okay. So this is an example, e.g. example, calculate the limit as x approaches 2 of 7x squared minus 3x plus 4. Two ways we could approach this. We could approach this first by splitting it up and saying, okay, well, this is the limit as x approaches 2 of 7x squared minus the limit as x approaches 2 of 3x plus the limit as x approaches 2 of 4. And then I can pop out the 7 and say, okay, that's 7 times the limit as x approaches 2 of x squared minus pop out the 3, limit x approaches 2 of x plus the limit as x approaches 2 of 4. You can pop out the 4 if you want and write it as 4 times the limit as x approaches 2 of 1. And then again, we can be really, really explicit here. Say this is the limit as x approaches 2 of x all squared minus 3 lim x to 2 of x plus 4 lim x to 2 of 1. So again, I'm just using my limit laws, right? The limit to split up over addition and subtraction. The limit law to pop out constants. The limit law about powers. Really just doing something here. And now I can say, okay, the limit as x goes to 2 of x, that's 2. So this is 7 times 2 squared minus 3 times, well, the limit as x goes to 2 of x. Again, that's 2. Plus 4 times the limit as x goes to 2 of 1. Well, remember, the limit of a constant function is just that constant. So this would be 4 times 1. So this is 7 times 4 is 28. Minus 3 times 2 is 6. Plus 4 is 22. Plus 4 is 26. But I think you would agree that this is more work than I would like to do. A better solution f of x equals 7x squared minus 3x plus 4 is a polynomial. So for any c, the limit as x approaches c of f of x should just be f of c, i.e., the limit as x approaches 2 of f of x is just f of 2, which is 7 times 2 squared minus 3 times 2 plus 4. And that just gets us right down to here immediately, which is 28 minus 6 plus 4, which is 26. And really, you didn't even need to write this stuff. You could just say, because f is a polynomial, we can calculate the limit by plugging in. These limit laws are useful for cooking up theorems. We don't really use them when we go to do calculations very often. We use them to say when we can calculate limits by plugging in versus not. Because this is a nice function, it's defined when x is equal to 2. It doesn't have any continuity issues because it's a nice polynomial. We can just calculate the limit by plugging in. We get this? Is this making sense?
Yeah.
Okay. So there's a nice theorem here. We can extend our theorem a little bit to say if f of x is any polynomial or rational function, then you can evaluate the limit of f of x just by plugging in. Your book calls it direct substitution. Just plug the number in. The question is, okay, so let's make some observations. The limit of f of x was the same as just plugging in x equals 2. Can we always do that?
No.
Yeah, unfortunately, the answer here is no. Sadly, no. You run into trouble when the thing you're trying to plug into is undefined at that point. And this is why so many of the graphs that we were looking at in last week's homeworks had holes. Remember where holes come from in graphs. Usually there's a factor top to bottom that cancels, and that's where you get a hole, stuff like that. So what we need to do is figure out how to handle those situations. And there's a nice result that's going to allow us to handle those. Sadly, no, because often when finding the limit as x approaches c of f of x, the value f of c is undefined. For various reasons, but usually 0 downstairs. The theorem that gets us out of this says this: if f of x is equal to g of x for all x values except right at c, then you can calculate the limit of f of x as the limit of g of x. And I'd like you to think about when you encounter equations like this. One function is equal to another function everywhere except at some particular number. You encounter these most often when you cancel a factor top to bottom. And that's what we're going to do most of the time here. So there's a classic example that I'd like to show you, and then we're going to look at some more challenging ones. Example. Let's calculate the limit as x approaches 1 of the function x squared minus 1 over x minus 1. If I tried to split this up and use my limit laws, or if I tried to just plug in, what you'll find is that, well, the bottom is going to be 0, right? As x gets closer and closer to 1, x minus 1 gets closer and closer to 0. So at a glance, this limit looks like 0 over 0, which is undefined. Be clear about that, right? 0 over 0 is not 1. 0 over 0 is undefined because there's a 0 downstairs. However, x squared minus 1 over x minus 1 can be rewritten as x minus 1 times x plus 1 all over x minus 1 times 1. You see what I did here? I factored the top, and then I recognized the bottom as just parentheses x minus 1 times 1. This is just algebra. Now I can cancel the x minus 1s as long as x minus 1 is non-zero, i.e. x is not equal to 1. As long as x is not equal to 1, this is the same as x plus 1. Try to see this in the context of what we just said. Here's a function. I'll think of this as like f of x. Think of this as like g of x. What we have here on the page is that this function is equal to this function as long as x is not equal to 1. In other words, everywhere except at x equals 1, these functions are equal to each other. So by our theorem, the limit as x approaches 1 of x squared minus 1 over x minus 1 is equal to the limit as x approaches 1 of x plus 1. And what you notice is that x plus 1 doesn't have any of the issues that the original function had. If you want to be really verbose about this, you could write it as lim x to 1 of x plus lim x to 1 of 1. And then as x goes to 1, the limit as x goes to 1 of x, that's 1. The limit as x goes to 1 of 1 is 1. So this limit is 2. These 3 dots arranged in a triangle, this stands for the word therefore. You'll see me use that a lot. Are we comfortable with this statement as a consequence of this statement and that theorem? Any questions about why these things are equal?
I get why they're equal, but didn't you say that x can't equal 1?
Yes. The trick is to remember that with limits, I don't care about what happens exactly at 1. I care about the pattern as x gets closer and closer to 1. So let me draw 2 graphs for you here. Here's the graph of f of x equals x squared minus 1 over x minus 1. And down here is the graph g of x equals x plus 1. They're not the exact same function, are they? They're almost the exact same function. The difference is f of x has a hole at 1. G of x does not have a hole. But the idea of the limit, what I want to do is find the limit of this function as x gets closer and closer to 1. The value of that limit is the y value of this hole. I can't calculate that by plugging in because this becomes undefined there. But this function is not undefined at 1. So I can find the value, the y value of the limit, which is the y value of this hole, by plugging x equals 1 into this other function, because they agree everywhere except at that point. So you're right. This function is not equal to this function everywhere. They're different. They're very similar, but they're different. This function's domain is all real numbers. This function's domain is all real numbers except x equals 1. But if I want to know what y value do I get closer and closer to along this graph as x gets closer and closer to 1, the easiest way to get there using algebra is to say, oh, well, that y value has to be the same as the y value that's actually on this graph. Because really, really close to 1, this and this are the same. It's only exactly at 1 that they differ. The limit doesn't care what happens exactly at 1. It only cares about what happens really, really, really close to 1. So the fact that these guys are not equal exactly at 1 doesn't bother the limit. The limits are still equal to each other, even though the functions themselves are not equal to each other at 1. I know it's very counterintuitive, We say, okay, these things are the same as long as we stay away from this point. And then when we calculate the limit, we end up plugging in that point here. But the idea is what we're after is the y value of this hole. I can't get the y value of this hole by plugging in because it's a hole. There's nothing there. So I do some algebra to find this very closely related function. It's so closely related that if I want to know what's the limit of this guy, I can take the limit of this guy instead. And taking the limit of this guy is easier because he doesn't have a hole. He doesn't have a discontinuity at 1. It's very subtle. And the thing to keep in mind is that the limit doesn't care about what happens at 1. It cares about what happens as you get closer and closer to 1. Does that make sense?
Yeah.
Yeah, I know somebody had I think was it Katie that had a little bit of an issue with this. I just want to make sure that we're covering the issue there. Does that resolve the question? Okay, cool. Yeah, these can be sneaky. They take some time to understand conceptually.
Yeah, as a graph, it makes more sense.
Yeah, I like the graph here too. I think the graphs are really helpful. All right, let me give you a slightly tougher example. And we're going to go through the same sort of procedure. So I'm going to use the variable h here. We're going to find the limit as h goes to 0 in 3 plus h quantity squared minus 9 all divided by h. Again, I cannot plug in 0. I can't solve the limit by plugging in. Because the function is undefined. At h equals 0. But I'm going to do some algebra to come up with another function that agrees with this function everywhere except at 0. In particular, agrees very, very, very nearby 0. Any ideas how I can do that?
Maybe if you like if you do like long division, try to simplify it.
Yeah, long division would do the job here. It's actually a little bit bigger of a hammer than we need. Let me show you how I would solve this. Long division is a good answer. It's just more work than we need because when we FOIL this out, you'll see that the cancellation is really fast. 3 plus h all squared is 9 plus 6h plus h squared. So my numerator is that minus 9, and my denominator is still just h. But of course, these 9s are going to eat each other up. This guy and this guy gobble each other up. So we get lim h to 0. And you want to be really disciplined about writing your equal signs, writing your limits. Good notation matters, and I'll be judging that a little bit more harshly in this class than I would in a non-honors class. So please don't forget to write your limits. When the 9s go, we have 6h plus h squared over h. From the numerator, I can factor in h. And that's something I always like to remind folks. I can't just cancel these h's like this. That shit don't work. The only time you can ever cancel top to bottom is if you have a common factor. So your previous step needs to be factoring if you're going to cancel something. When we factor in h from the top, we get h times 6 plus h, and the bottom is h times 1. Right? And writing that 1 is just to remind us that when we cancel, the bottom doesn't become 0, it becomes 1. And what I'm left with is lim h to 0, 6 plus h over 1. I won't write the over 1 in this line. So here is my original function, my f of x, or in this case, f of h. And here is my very closely related function, g of h, that agrees with f everywhere except exactly at 0. But as you sneak up on 0 in this guy, you're going to the same y value that you'd get as you sneak up on 0 in this guy. This may not be equal to this exactly at 0, because this is undefined exactly at 0. But when h is 0.000001, this is the same as this. And as those h's get smaller and smaller, these values still match. So the pattern in the y values is the same, which means the limits are the same. And then this limit down here, I can calculate this by direct substitution. This is 6 plus 0. So I know at the end here, it's counterintuitive. We are plugging in that thing we said we couldn't plug in, but it's just a trick for calculating the limit. It's just a trick for saying what this gets closer and closer to as h gets closer and closer to 0. And of course, 6 plus 0 is 6. So problems like this are going to show up a lot in this class, especially like before you get to chapter 3. This is an archetypal or a very characteristic, a very good example of the types of problems we'll want to solve a lot. You're trying to take a limit. The bottom's going to 0, so you have to do some algebra, cancel the factor from the bottom that's making the bottom 0. Then you calculate the limit by plugging in. The concepts are important. Thinking about those graphs are what's going to save the day. If f of h is 3 plus h quantity squared minus 9 over h, then the graph of that function looks like this. My related function, g of h, is just 6 plus h, and his graph is the same, it just doesn't have the hole. So while I can't calculate this limit, the limit as h goes to 0 here, algebraically by plugging in, looking at the graphs, you can see that that limit would be 6, which is the same as the actual y value on the graph of the canceled version. And that's the magic behind this algebra. How do we feel about this?
Yeah, makes sense.
Good. Are there any questions or concerns here? Sweet. Okay. So you may or may not recognize this limit as a limit that defines a derivative. It's something that's coming from a difference quotient. We will deal with those very soon, but there's some other details I want to talk about regarding limits before we do. Specifically, algebra tricks. Oh, let's do this one. Plus minus 3. I would have thought we'd go with the t there, but t squared it is. Okay. All right. I want to take the limit as t goes to 0 in this function. And this time I'm not going to draw any graphs. We're just going to do it using algebra. Again, if I try to plug in, I get 0 downstairs. Because that makes the bottom 0, which is no good. And this time, I can't really like expand and factor the numerator because there's no way to like expand a square root. But there is an algebra trick for getting rid of square roots in the numerator when you see expressions like this. Is anybody familiar with a trick for getting rid of square roots like these? I can't just square it. Squaring it's a good idea, right? I understand why we might want to do that, but if I just jump in here and square this, I'm going to change the function. It wouldn't be the same function anymore. But the sort of things we can do are like add and subtract numbers or multiply and divide by the same quantity. Is anybody familiar with the multiply by the conjugate trick? So squaring it, reasonable idea, but I can't do that because it changes the function. Right? Like f of x equals x compared to f of x equals x squared. I wouldn't expect those to have the same limit because they're different functions. But if I multiply by the conjugate, so I leave this piece alone for now, but I'm going to multiply by something. I'm going to multiply by t squared plus 9 under the square root plus 3 over t squared plus 9 under the square root plus 3, like this. Notice that this whole thing that I'm slapping on here is equal to 1. I'm multiplying my function by the number 1, just in this really ridiculous form. So multiplying by this doesn't change the value of the function at all. It's still the same function. This thing is equal to this thing, because this thing times 1 is really what I have down here. This whole piece is the same as the piece above because this piece is really just 1. But it's a useful way of writing 1 because now if I multiply these fractions, numerator times numerator, denominator times denominator, like fractions always multiply. My calc professor would make a bad joke here. He'd say, I'll do the bottom, you do the top. All right, so I did the bottom. We have this times that. Upstairs, we need to be more careful, right? I'll have the square root of t squared plus 9 times the square root of t squared plus 9. Like these are my firsts. These are my inners. These are my outers. And these are my lasts. I'll write this all out. This is t squared plus 9 under the square root squared. That's my firsts, right? Root t squared plus 9 times root t squared plus 9. My outers are plus 3 times the square root of t squared plus 9. And I need more space here. My inners are minus 3 times root t squared plus 9. And my lasts are negative 3 times positive 3, that's minus 9. Notice that the middle two terms add up to 0. That's dope. And that now I do have the square of that square root. That piece that we wanted so badly does show up here. That gets rid of my square root. So I have equals lim t to 0 This piece, when I simplify it, just becomes t squared plus 9. All of this shit in the middle is 0, and my lasts are minus 9. So this is what I get. Is everybody following this algebra? Similar to the last problem, I have a plus 9 and a minus 9 that will eat each other up. And what remains is lim t to 0 t squared divided by t squared times the quantity square root t squared plus 9 plus 3. And now the t squareds can cancel. So I get lim t to 0. I want to point out that canceling the t squared from the bottom was the whole goal. That's what I needed in order to make this work out, because that's the piece that was making my original function undefined at 0. So now I'm happy. My numerator is just 1. My denominator no longer has a factor of t squared in it. It's just the square root of t squared plus 9 plus 3. And this limit I can evaluate by direct substitution. This limit no longer has the problem of that t squared. So if I plug in 0 for t, I will get 1 over the square root of 0 squared plus 9 plus 3, which is 1 over the square root of 9 plus 3, or 1 over 3 plus 3, which is 1/6. This trick is called the multiply by the conjugate trick, and we'll use it quite a bit in this class. Not as often as the factor and cancel trick, but this multiplying by the conjugate is often a good idea. If you need to evaluate a limit, but there's no obvious way to get rid of the square root that's causing the problem, try multiplying by the conjugate. All right, I'll take a second. You can copy this down, make sure you get everything nice and clear in your notes, and then any questions you have, we can address. Questions on this? Okay, so most of your homework this week is going to be very straightforward stuff. Some of the problems you'll be working from a graph. You'll be able to infer the limits you need from the graph, maybe with some combination of the limit laws. For example, there's my textbook. If we look at this guy, let's look at example 1 in the textbook together really quickly, and we'll wrap up like this. If I want to find the limit as x approaches -2 in the apparatus f of x plus 5 times g of x, I would first split that up as the limit as x goes to -2 of f of x plus the limit as x goes to -2 of 5 times g of x. That was our first limit law that they split up over addition. Then I can pop out the 5, right, using the rule that constant multiples pop out of limits. And then I turn back to my graph to figure out what each of the limits are that I need. Looking at my graph, The red here is f of x, the blue is g of x. If I want to find the limit as x goes to -2 of f of x, I look along this graph and ask what are my y values getting closer and closer to as my x values get closer and closer to -2. Well, that's the y value of this hole right here. Remember, I care about the pattern, what happens nearby, not what happens exactly here. This doesn't matter. What matters is what are these getting closer and closer to, and that's definitely 1. So the limit as x goes to -2 of f of x is 1. And I play the same game for g of x. As x gets closer and closer to -2, I'm looking along the blue graph. The height, a little guy walking along this graph, his height is getting closer and closer to -1. So this highlighted piece here is going to -1. So the whole expression, this piece is 1 plus 5 times -1. So we get 1 plus 5 times -1. That's -4. These will probably be the easier problems in the homework set, where you use limit laws and a graph like this to figure out a slightly more complicated limit like these. The harder problems in the homework set will be like the ones we just did here, where you don't have a graph. You need to use some clever algebra. Your first thought should be the sort of thing we did in the first example like that. See if you can factor, expand, factor, cancel. If you have a square root like this, try multiplying by the conjugate. Whatever your expression is, you should first try plugging in, right? Like the very first example we did with that polynomial, where we could just take the limit by plugging in. Try that first. Always try that first. But if the bottom is 0, like in this one, you're going to need to do some algebra. And exactly what that algebra is depends on the shape of the function you have here. If you run into any trouble on any of these, don't hesitate to send me a Canvas message or come by an office hour. I do have an office hour this afternoon. You're more than welcome to bring any homework questions there. In parting, I would like us to think about continuity a little bit. What makes it possible for us to evaluate the limit here by plugging in is the fact that this is a continuous function. Specifically, this function is continuous at t equals 0. The original is not continuous at t equals 0. It's undefined there. Similarly, this example, what allowed me to take the limit at the end is that this function g of h, 6 plus h, is a continuous function, specifically continuous at 0, continuous where I'm trying to take the limit. The original was not continuous at 0. It was undefined there. In calculus, we define a function to be continuous if the value of the function is equal to the limit of the function. So I'm going to leave you our last minutes with the definition of continuity. Next time we will pick up here. This is section 2.5. Continuity is something that happens one point at a time. We say the function f of x is continuous at the number x equals c if the limit as x approaches c of f of x is what you get by plugging in the number c. A quick note, this can fail in 3 ways. It's possible that the limit as x approaches c of f of x does not exist. If something does not exist, I can't say it's equal to something else. Remember, this limit can fail to exist by having the left and right limits being separate from one another. It's possible that f of c itself does not exist. Right? Maybe the limit exists, but the function isn't defined there, i.e. you have a hole. And the third possibility is that both the limit and the function value exist, but maybe they're not equal to each other. So next time we're going to talk a little bit more about continuity. I'm going to explore some of the consequences of this definition. We'll look at some examples where each of these three things happen in varying combinations. And then we're going to talk about limits at infinity. We're going to jump to section 2.6. So next time we'll look in more detail at section 2.5. And then we'll talk a little bit about limits at infinity. The other thing we need to talk about is section 2.4, which is the precise definition of a limit. I haven't put any of those precise definition of a limit, section 2.4 problems in your homework set yet, but I will add some after we have that conversation. So your homework for this week is going to pop open in just a second as soon as we finish class, but be aware that I'm going to add a few problems to it after we get through 2.4. I just want to make sure that we cover the really important stuff for the rest of the class, which is 2.2, 2.3, 2.5, and 2.6, before we get lost in the nuts and bolts of 2.4, because 2.4 can be a little bit tricky. Any questions for me before we sign out for the day?
Yeah, Mr. Felsiger, Professor Felsiger.
Sure, yeah.
I was wondering if I could tell you right now the student teaching section that I wanted to teach, if it's okay right now.
Yeah, that's fine. Yeah, what's up?
I wanted to do section 3.10, linear approximation.
Okay. Do me a favor. I'll go ahead and add this to my spreadsheet right now, but send me an email just so because I'm keeping track of those things in a specific place. Send me an email or a Canvas message letting me know the same thing. That way I've got it in file everywhere I need to have it for organization purposes, okay?
All right, got it.
All right, thank you, Julio. Anything else? Other questions, comments? Anybody else want to lay claim to any particular student teaching? All right, then remember, by Friday this week, I need both your student teaching and your honors project topics. So please be thinking about those. I don't, Thomas, thank you. I did see, I've got some emails that I haven't responded to yet. I'll be getting to those a little later this afternoon. So if you've already emailed me, don't stress. I promise I will get back to you about that later today. Alrighty then, I'm gonna go ahead and end our meeting here, guys. I hope you have a lovely rest of your afternoon. Do take a look at that homework. It's just about to open up, or it should be open within a few seconds here, and I will see you on Wednesday. Have a good one, guys.